Okay, John, I'm just going to briefly go over, I'm not real sure where we left off, and I tried to send a video earlier. I tried to just record my flip chart, but evidently that didn't work. So I'm just going to quickly summarize. We took a test on polynomial functions, and that is like, we've already done like quadratic functions where the graphs were either just parabolas facing up or down. And now we're going to get into polynomials where the graphs can look anything like this, or they can have multiple turns and have multiple different things. So some basic things that we figured out when we did this was that if a function has an odd degree, and I'm just making up the rest of this, doesn't matter, but the highest degree, meaning the highest power of that function, is the degree of the function. If that highest power is an odd degree, if it's x to the third, x to the fifth, it doesn't matter what's in front of it, x to the seventh, whatever, as long as that highest power is an odd degree, what we found out was that it was going to have opposite ending behavior, meaning where it started, one end was going to be going down, one was going to be going up. It could have multiple turns in it, but it was going to end in opposite directions. So it could also start positive and end negative. So if a function at any point in time ends where one end is going down and one end is going up, it must be an odd degree function because it has opposite ending behavior. Likewise, if it has an even degree, so if it was 4x to the 10th plus 2x squared minus 6, and I'm making that up again, if the highest power of x is an even number, then it's going to have the same ending behavior. So if it's an even power, it's going to have same ending behavior. So that means it's either going to look like this, where they both end going up, they both end going down, or again, we could have multiple turns. It doesn't matter as long as they both end the same. So if they both end going up or they both end going down, then it must be an even powered function and therefore have same ending behavior. So if I just gave you some graphs to choose from, and I just drew some, then without even being able to see the function at all, or without even being able to tell the equation at all, I should be able to tell some things about it. Well, the first thing I should be able to tell is if it is an even degree function or an odd degree function. One's going down, one's going up, so this is an odd powered function. One's going up, one's going down, so it's ending in opposite directions, so it's an odd degree function. They're both ending going up, so they have the same ending behavior, so this must be an even degree function. They're both ending going down, which is the same, so again it's an even degree function. And one's going down, one's going up, so it's also an odd degree function since it's ending in opposite behaviors. So also from that we talked about ending behaviors. So we said as x goes to negative infinity, what is happening to the function? And what I mean by that is as I continue to go on the x-axis, as I go farther and farther left, so here's x equals -1, -2, -3, -4, all the way out here to negative infinity. If I went as far to the left on this x-axis as I could possibly go, where would this function continue to go? Well, as I continue to get farther and farther to the left, this function is going down, which means it's approaching negative infinity. As I continue to go to positive infinity on the x-axis, so as I go out here to the right and I go out, 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 and it continues to go positive infinity, now where is the function continuing to go? Well, it's going to continue to go up, which we would consider that to be positive infinity. This is what I refer to as ending behavior. So basically, as x goes negative infinity, that means as we go farther to the left, on the very far left end, where's the function going? Well, it's going down. As I go positive infinity, this is considered on the right-hand side of the graph. Then where's the function going? Well, on the right-hand side of the graph, the function's continuing to go to positive infinity. So this is what the ending behavior of this first polynomial graph would look like. For the second one right here, if I ask for the ending behavior, so as x goes to negative infinity, which remember is basically to the left, where is the function going? Well, as I go to the left on this graph, where's the function going? It's going to continue to go to positive infinity. As I go to positive infinity on the x-axis, which basically just means as I go to the right, where's the function going? It's going to end up going to negative infinity. And again, since these are opposite ending behaviors, one positive, one negative, we know, and that reinforces that this must be an odd degreed function. For the third graph, if I want the ending behavior as x goes to negative infinity, as x goes to the left, so as I go to the left-hand side of this graph, where's the function going? Well, the function is going up. It's going to positive infinity. If I go to positive infinity, which means as I move to the right on this graph, where's the function going? It's also going up. So again, they have the same ending behavior. They're both going positive, which it reinforces that this is an even degree function. For number 4, as I move left on the x-axis, as I go to the negative infinity or to the left, where's the function going? And as I go to the right or to the positive infinity, where's the function going? So as I go left, the function's going down, so that's negative infinity. As I go right, the function's going down, which is also negative infinity. Again, same ending behaviors, reinforces that it's an even degree function. There's one more thing we can learn about this, and that is, if I have the function, not only if I look at the degree, well, first of all, looking at the highest powered, I know that that's an even number, so immediately I know that it's going to have the same ending behaviors. So either it's going to both end going up or it's both going to end going down. And again, there could be multiple turns in the middle, but I'm only talking about the ending as far left and far right. The way that I can tell which it is, whether it's both going to be going up or both going to be going down, is now to look at the leading coefficient. This leading coefficient is a negative number. So that means on the far right-hand end, it's going to end negative because my leading coefficient is negative. So as I move over to the far right-hand end of my graph, it's going to end going negative, which means it must be this graph. So therefore, it's both ending negative. I would know that my graph is going to be the one where they're both facing downward. If I gave you this, and then again, the first thing I'd look at is the degree. Immediately, since it's an even degree, I know that they're going to have the same ending behavior. So again, they're either going to be both going up or they're both going to be going down. And I don't know how many turns are in the middle, but I know that their ending behaviors are going to be the same. So this time I'll look at my leading coefficient and it's positive. That means the far right-hand side is going to end positive. This number is going to tell me what's happening on the right-hand side. So the right-hand side is being positive. So this one's the one that has positive on the right-hand side. So this must be the function. It must have, both of them must be going to positive infinity. Now where this really comes in handy is when I'm looking at an odd degree function. So again, I will look at my degree. First of all, oh, that's supposed to be positive 3. As I look at my degree, it's a third degree function, so immediately I know that it's an odd powered. So I know that it's going to have one going up and one going down. I just don't know if it's going to start negative and end positive, or if it's going to start positive and end negative, and I need to know that to know the ending behavior. So I look at my leading coefficient. This tells me what's happening on the right-hand side, and this says the right-hand side is a negative number, so the right-hand side is going to end going down. Well, here's the right-hand side, it's ending going up. This right-hand side is ending going down, then this is the shape of that graph. So at least I know that the beginning behavior, as it goes to the left, must be going to positive infinity. But the right-hand side, as x goes to positive infinity, the function is going to negative infinity. And that's simply because my leading coefficient was negative. So if I gave you some graphs and I said match the function with the graph, the only thing I'm interested in looking at every single time is the degree and the leading coefficient. So now if I have to match them with each one, I can look at their traits. and rule them out. So immediately the first one I look at, this is an odd degree function. As soon as I see an odd number, I know that it has opposite ending behavior. Well, the only ones that end opposite has got to be C or D. They're the only ones going up and down, up and down. These are ending the same. So it's got to be C or D. Well, now it tells me that the leading coefficient is negative, which means on the right-hand side, it's going to end negative. If I look at the right-hand side of this graph, the function's going up, so that's positive. So this is the only one that on the right-hand side that's going down, so this one would have to be D. 6th degree means it's an even degree, so it means I have same ending behavior, so it's got to be A or B. Positive leading coefficient means the right-hand side is going to be going up. This is the only one that has right-hand side going up of my two same endings, so this one has to be A. Odd degree, it's got to be C or D. Leading coefficient is positive, which means it ends on the right-hand side positive, so it's got to be C. Even degree, they're ending the same. Leading coefficient is negative, the right-hand side's going down, it's got to be B. The only other thing in this section that we did was we evaluated functions. So if I gave you f of x is equal to 3x squared plus 2x plus 1, and I ask you to do f of negative 3, then all I'm going to do is anywhere there's an x, I'm going to fill in a negative 3 where the x was. And then we're just going to evaluate this. So this would be 3 times positive 9 plus negative 6 plus 1. 27 plus 6 plus 1. 27 plus 6 is what? 12. 32, 33 plus 1, which would be 34. So f of negative 3 would be 34. Well, we're going to take it a step farther, and instead of f of negative 3, what if I ask you to find f of 2x? I'd do the same thing. I'd repeat this function again, except when I got to the x, put parentheses. And inside the parentheses this time, instead of a negative 3, I'm going to plug in a 2x. You have to follow order of operations. We would do this first. Well, 2x times 2x is 4x squared plus 4x plus 1, which is 12x squared plus 4x plus 1. And that's as far as you can go. One last thing on that one, 3x squared plus 2x plus 1. Is if I ask you to find f of x plus 2. Then we're going to do the same thing, but inside the parentheses this time we're going to plug in x plus 2. The only thing to be careful of is that x plus 2 squared means this, which means we have to FOIL this. Which is going to be 3 times x squared plus 4x plus 4, which is now distribute. And so now this is going to be 3x squared plus 12x and 2x, which is plus 14x, plus 12 and 4 is 16 plus 1, which is 17. So f of x plus 2 is equal to that. That's pretty much all that's, actually that's not all that's on there. That's everything except division of polynomials. And I don't know if you were here for that or not, so I'll do a separate video for that. And then that will get you ready for the polynomial test, and hopefully that will help. And I can send some practice problems on each of these as well.